What I want to cover in this lecture is essentially how to think firstly about Fourier spectra. This is a terminology that you've not encountered before, the spectrum of a signal. And then we want to talk about Fourier series in time. So we've been mainly focusing on Fourier series in X. This is the natural way that we've developed it throughout the course, f of x. But you can also think about it as f of t. And in doing so, nothing has really changed. You're just looking in time instead of looking in space. But some of the terminology changes. So instead of talking about wavelength, right, people will talk about frequency and period. So period in time is the same as wavelength in space. It's just a different terminology. The next thing I want to show you is how you can generate sound, right? How do you go to MATLAB and then create a sound from a signal and then play it on your audio speakers. And in doing so, you're going to try to understand this correspondence between the mathematics that you've been doing, the Fourier series that you've been doing, and then things which are much more intuitive, like sound. Okay, so let's do a bit of review on the notion of a spectra and the notion of a Fourier series. Okay. So in example 12.1 of your notes, you looked at this square wave, right? So this was a function that was -1 and then 1 and then repeated. And this was on the x interval, and I recall that we did it from -pi to pi. And we wrote down the Fourier series of this function, this f of x, and we derived the Fourier coefficients, and you derived the lambda n, okay? And you remember before I mentioned that sometimes you call the lambda n's the eigenvalues of the problem. The bn's are the Fourier amplitudes of the problem. So the bn's tell you how the different sines, and an for the cosines, are weighted, which sines are large and which sines are small. And in this case, for this particular function of the square wave, you had a function which was either 4 over n pi for the amplitude if n was even, so here lambda n is equal to n. And it was 0 if 4 over n pi if n is odd, and 0 if n is even. Okay. Now, another way of representing this information is for me to plot these amplitudes bn, and then plot the eigenvalues lambda n. So I could make a plot here of n versus bn. And if I were to do so, then n would go through 1, 2, 3, 4, 5, and so forth. And at every odd number, it's essentially 4 over n pi. So you can imagine the graph of 1 over n looks something like that. And essentially, at every odd number, you get a dot. Like that. And at every even number, you get zeros, but we won't bother plotting that. Okay? Okay, so this sets up a very interesting and powerful correspondence. On the left here, you have real space. You have basically, you imagine waves in space, x and f. On the right, this is what's called Fourier space, or the spectra. Okay, I'm going to change the notation a little bit here, just so it's more typical with what's used. And instead of n's being my index, I'm just going to call them k's. Okay, so k is the index now. Because in later applications of Fourier series and what's known as the Fourier transform, you often use k as the variable, as the Fourier variable. So here we're going to use k and we're going to index over k. Okay, I'll erase this. So as I said, you can think of this correspondence between this we call real space. So I'm going to define real space as basically x and f of x. You can think of, I'm going to define real space as the position x and the height of the function f of x. And I'm going to define Fourier space as k and ak, or bk. AK or BK. In this case, we don't have any AKs, but we can just use the BK. And one of the punchlines of this course is that in many ways you can think of space, instead of thinking of it in terms of real space, signals in real space, waves in real space, you could think of a universe where everything is represented in Fourier space, k and bk. And in many ways, if I were to tell you the information of the signal in Fourier space, each k and the weighting of the sinusoidal bk, you can reconstruct real space simply by taking the Fourier series. You form the Fourier series and you reconstruct the real space signal, right? And so that is this powerful correspondence. Instead of working with x and f of x, you can work with k and bk and the basis functions. This is very similar to those concepts that you learned in your algebra courses about vector spaces, right? If you have a basis, then you can represent elements of the vector space in terms of the basis weighted in a certain way. And so you don't have to think of individual vectors. You can work with basis vectors instead. And so here the basis vectors are sines and cosines. The weightings are given by the amplitudes bk and ak. Okay? So this is what we call Fourier space. And this is also what I'll define to be the spectrum. Okay? Now, you're going to get different definitions of what spectrum is. Sometimes they're a little bit vague. If you go online, you try to search for spectrum. So in this course, I'm just going to call the spectrum as this pair of coordinates, k and bk. It's the spectrum of the signal is the weightings on the Fourier modes, on the sines and the cosines. Okay, that's what we call the Fourier spectrum. Okay. The question has come up, what's the appeal of working in Fourier space? And that's an excellent question. The appeal is that in working in this space, you may get a better intuition of the signal. The signal may be very complex, right? And this is what's going to happen with sound. Sound is going to be a very complex signal, but by thinking of it in this spectral space, the spectrum or the Fourier space representation of the signal, you can essentially extract key information from the physical world. Okay? All right, so that was the essence of this little subsection for you to become familiar with us talking about notions like Fourier space or spectrum. So whenever you hear spectrum, you just think these are the amplitudes of my sines and cosines for a given signal. Or whenever I say Fourier space, you think of A, BK, or or K. So you think of K, BK, or K, AK. Okay? That's the way you visualize Fourier space. Different signals will have different profiles here. Now, one universal aspect of a good profile is that it should decay in time. It should decay as k increases. And the reason why it should decay as k increases is that if you had a signal where the spectrum increases as k goes to infinity, well, firstly, that doesn't bode well for the convergence of your Fourier series, right? Because the amplitudes are getting larger and larger. But also, it's a bit of a funny signal because it tells you that the signal is composed of very highly oscillatory sines and cosines. Okay, and again, that is related to the convergence of the Fourier series. So most of the spectra that you'll see for a signal, for a well-behaved signal, will look something like this. It's going to decay as this number k increases. Okay. That's right. So the question is, if you have AK and BK, do you have two profiles for one in real space? No, not really. So I have one real space profile, but you can think of one real space profile as requiring both a KAK and a KBK, sines and cosines. You need both sines and cosines to represent all the possible signals you can have. This is, in a sense, the Fourier decomposition theorem. It tells you that you need both AKs and BKs. So you should think of Fourier space as decomposed into a K, AK, and BK. You can think of it as a triplet of coordinates. Actually, the representation that your computers use is not with an AK and a BK, which is real valued. but they combine the two together and they work with complex numbers instead. And so you have a complex number here instead of the individual AK and BK. And this was one of the problem set questions that you studied previously during the Fourier series part, that there was a question where it showed you that there's a way to represent Fourier series in terms of complex numbers. Okay, so the next thing we're going to talk about is just how you convert from essentially sound, things that you hear, to the digital representation in your computer. Okay, and this is the cartoon that I have. And it's an interesting question. It's always interesting to ask students what sound is. It's one of those concepts that you might have heard about, or we all know what sound is, but you don't really know how to define it mathematically or how to define it scientifically. Okay, so let's make a sound, right? So we're going to take a string and then we're going to pluck the string. Okay, so this is something that you've learned how to model in this course. You've learned that if I want to model this deflection u, then I have a wave equation utt is equal to u c squared uxx with corresponding boundary conditions at the ends. So for example, I'm going to pin the ends of my string, I'm going to pluck the string, and I have the machinery now to study the solutions of this problem using Fourier series, right? And so this is a plucked string. So this is a mechanical vibration. And there are other ways that you can create mechanical vibrations. You can hit a drum, right? You can make a sound with your vocal cords, right? But in any case, essentially what you're doing is some sort of vibration in space and in time, okay? So the next thing you do is you pluck the string, and what happens is that this disturbs the air around the string, right? So that disturbs the molecules, the constituent molecules of air, right? So that's this picture here. You can think of the air molecules as little particles, and that basically creates a wave in the air that travels from one location to the next, okay? From the string to your ear, or from the string to your computer where the sound is recorded. So these are the molecules. So this is, and this system as well can be studied using partial differential equations, okay? You can study the density of air, rho. If I call rho the density of air, I can write down a partial differential equation which describes the evolution of this disturbance, okay? And you'll notice that the equation for the air density is essentially the wave equation. So in fact, the two are the same equations. This, though, is the speed of sound. Okay, so whereas this c is the speed which is characterizing the mechanical properties of the string, this is the speed of sound in air, or it might be the speed of sound in water or some other media. Okay, but basically you can study them using very similar machinery to what you did. And the other thing that you might intuitively suspect is that the solutions of this problem, the Fourier series decomposition of this problem, which you know how to do, will somehow feed into the solutions of this problem, which will be of a very similar form. Right? And that's something that you can just take as an assumed idea, that any waves you generate on this string here will essentially be the same type of waves which are observed in the air itself, just with slightly different speeds, because the speed of propagation is different between the two mediums. Okay, this disturbance in the air eventually reaches your eardrum, or it reaches your computer's microphone. Okay, and that's what this picture is. This is the microphone. And the question is, well, what is a microphone, first of all? Okay, a microphone is nothing more than, it's basically a drum. It's a very thin device which has some sort of drum or some sort of device that can oscillate when it detects changes in the air pressure. That device oscillates, which transfers the oscillation basically to a magnet, right? And the magnet is surrounded by a wire, and when the magnet vibrates, that essentially produces electrical current in the wire, which is then transferred to your computer. So that current goes in your computer, and that's detected as the electrical signal. That's essentially what a microphone is. It's a device for transferring mechanical vibrations, sound vibrations, into the electrical signal. Okay? And then finally, that makes it into your computer, and you can think of it as a plot in time of this vibration, right? So this is what we're illustrating here with f of t. F of t is the signal which came from the string itself, and it's just a series of, it's a very messy oscillatory signal, right? This is what you'll see if you open up an audio program and you try to record some audio, okay? So these are, in essence, characterized by the vibrations of the drum, of the microphone, which is then characterized by the molecular movement of the air, which is then characterized by the string. So this is how you go from a mechanical vibration to a digital signal. Okay? Good. So the next thing I need to explain to you is this f of t. Okay? So as I said, rather than looking at Fourier series in space, we're now thinking about Fouriers in time. This is not an unusual thing, because when you wrote down the Fourier series solutions of the wave equation, u of xt, you had already worked with Fourier series in time. If you remember, you had u is a sum of sinusoidals in x. This was sine of nx, for instance, times an sine or cosine of nt plus bn sine of nt. Okay, I've not written the factors here, but you had already worked with Fourier series in time before. But I want to talk a little bit about the change in terminology when you go from Fourier series in space to Fourier series in time. And in particular, the concept of a hertz. Okay, so let's talk about a very simple sinusoidal wave in time. Okay, let's look at f of t equal to sine of 2 pi f times t. Okay, and I've written it in this particular way with the 2 pi and the f here, just because this is the standard way you would think of signals in time. This f here is known as the frequency. Okay? Usually we have, instead of sine of 2 pi ft, we have sine of k times x, and we call k the wave number. Okay? Here, f is called the frequency. Now, the units of frequency are measured in inverse units of time. So if time is measured in seconds, then f is measured in 1 over second. Okay? So this has units of 1 over second. You know, because whatever the units are, they have to be cancel out, because the input of the sign needs to be unitless, needs to be non-dimensional. So if time is measured in seconds, then the units of this frequency should be measured in 1 over seconds. And this unit of 1 over seconds is called a hertz. Okay, so when you hear the word hertz, that's what it means. It basically just means 1 over seconds. Unit is 1 over seconds. Okay. Now, what does this signal look like? Well, the wavelength of this signal is basically, you remember whenever we did k times x, the wavelength is just 2 pi over k. So in this case, it's 2 pi over 2 pi times x. So it's 1 over x. Okay? And when you deal with signals in time, rather than call things wavelength, you would call this the period of the signal. Okay? So rather than call it a wavelength, which you would call 2 pi over k the wavelength of this signal in space, when you deal with time, you call this the period. So the period here is 1 over f. Okay? Let's take a very simple example. So if f, for instance, is 100 hertz, okay, then one wavelength, or a period, is 1 over 100, okay? Which means that in 1 second, the signal will repeat itself 100 times. That's the other way of thinking of hertz or frequency. It's the number of times that the signal repeats itself after one second, after 1 unit of time. Okay, so for 100 hertz, the signal is going to repeat itself 100 times. Okay, that's all we need to know about this change from terminology, from wavelength to period, from wave number to frequency. Okay, right. So the last thing we need to know before we try to make a sound on the computer is this concept of a sampling frequency, right? So when the computer essentially records the signal from the string to sound to the vibration in the air into the microphone, it can only do so at a certain frequency, right? Because it can only record at discrete moments in time. This is what's known as a sampling frequency. Okay, so you can look up, for example, your computer sound card, or you look up your microphone or other devices, and they will have some sort of sampling frequency, which is basically the number of times the computer records the signal as it's coming in. Okay, so so the sampling frequency is basically the number of times the signal is to be recorded, or the rate that is recorded, called the rate. So we're going to be working with, so the default sampling frequency for the MATLAB for the MATLAB function we're working with is 2 to the 13 hertz. And 2 to the 13 is 8192. Okay, so that's basically the rate that is going to record the signal. This is going to become quite clear when we just work with our numerical example. Okay, so let's do that now. We're going to first share my screen here. So what I want to do is I want to make a vector in time and a vector in time of a signal. I'm going to make up a signal, and the easiest signal that you can make up is just a simple sine wave. Then once we've made that up and we've kind of created a vector for it, a digital representation for it, we're going to send that out through our speakers. Okay. So the first thing we need to do is we need to define the sampling frequency. And as I said before, the sampling frequency that is used by default by the little snippet of code that we're going to use to output to our speakers is 2 to the 13, right? But different devices will have different sampling frequencies they can cope with. We're going to make a signal for 8 seconds long. So this is the t is equal to 8. Okay? And so we're going to have to create a vector in time, a set of of measurements in time that run from 0 to 8, right? With a spacing of 1 over the sampling frequency. So let's do that. So you're going to make a vector from 0 to 8, capital T, with 1 over that sampling frequency. And then we're going to make our signal. So our signal will be just a regular sine wave. It's going to be 2 pi. And then we're going to measure, we're going to try to make a sound at a certain frequency. So I'm going to make the frequency 440 hertz, 440 times time. So there's our sine wave. It has a frequency of 440, okay? And if I Now if I run this, and I look at the representation I've created, so let's just look at the coordinates that we've made, or the vector that we've made. We've made essentially a vector with 65,000 elements, around 65,000 elements, right? And so this is the original time vector. The time vector should run from 0 to 8, has 65,000 elements with a spacing of 1 over the sampling frequency. And if I plot that signal, it might plot or it might not plot. It's extremely dense, you can see, because it's got so many elements. So instead, we're just going to change the limits from 0 to, say, the 100th element, say the 1000th element of the time vector. Okay, and there you are. So there's our sine wave. It's extremely compressed because it's oscillating so rapidly. So now you can use the MATLAB sound function, and hopefully this comes out in our speaker. And the MATLAB sound function just takes two inputs. One is the signal itself, the F, and the other is the sampling frequency, which we've already chosen to be Fs. So now let me play this, and then what you should hear, if it's going to come out in the microphone, is a 440 hertz signal, which is being played for 8 seconds long. Okay, there you go. That's right. So someone said, oh, I can tune their violin, and this is exactly right. So 440 is a well-known frequency in music, because this is often the way that musicians will calibrate their instruments. They'll play the 440 hertz note, and this is what's known as an A note in music, and you use this to basically tune your instruments. Okay? Now, on a violin, there's actually 4 strings on a violin, right? And the second highest string is the 440 hertz string, the A note, right? The highest string is what's called an E note, right? And this has a frequency of around 639.3, if I remember correctly. 639.3. So if I play that instead, it should sound like an E note. Okay, there's your E note. Okay, so now you can imagine that we can create all sorts of notes just by creating different combinations of sine waves. So for instance, let's create an A note, 440 hertz, and we're going to play this together with an E note. So we're going to weight it. So we're going to take 0.6 of an A note and add that to an E note. And we're going to make the E note a little bit stronger at 630. It's actually 659. I was wrong. 659.3 is the frequency of an E note, I think. And we're going to play it only for 5 seconds, because 8 seconds might annoy me a little bit. So let's play that now. So this is a combination of a Fourier signal, which is 0.6 amplitude for the 440 hertz vibration, and then an amplitude of 1 for the 659.3 vibration. These amplitudes, you can imagine, are normalized in some way. So when MATLAB takes the signal and sends it out to your speakers, it has to renormalize these signals. So you're not too concerned about the absolute magnitude of those signals. It's more how relative they are to one another. Here we go. Okay, so there's your A note, a little bit of an A note, and then a little bit of an E note. Okay? Right, so this is essentially what is shown in your lecture notes. I'm just going to duplicate your lecture notes a little bit more closely here. So I'm going to call this the F2 signal, and then I'm going to make an F signal, which is the A note. And so we're going to keep that at amplitude of 1. We'll hold off from playing it for a second, and then we'll plot the two graphs together. That's what these next few lines do. And they just do it in a slightly fancier way. So let's plot that. Okay, here we go. So on this plot, you see basically two graphs. One graph is the signal for the 440 hertz, the 440 hertz signal. So this is plotted in T and then F. And in the solid lines you see is just that very basic sine wave, 440 hertz, 2 pi times 440. On the other hand, you also have a dashed dotted curve, and the dashed dotted curve is the secondary signal. It's the one which was composed of 0.6 of the 440 plus 1 times the signal for the 659.3. Okay? Now, there are other ways of representing this kind of graph. And for example, you can plot things using a stem plot. But this is just for, I think this is just more for curiosity's sake. Because the signal is discrete in time, this is perhaps a more representative picture of what you should really think about. So this is a plot of F2, the secondary signal, which was composed of the two 440 hertz signal plus the 659.3 signal. And because it's being measured at discrete moments in time, this is now just what's called a stem plot. Okay, but this is just for curiosity's sake. All right, the last thing. So now that I've covered everything from a mechanical vibration to how it's digitized in your computer, how it essentially vibrates the microphone and that's transferred to electrical signals. And we've gone the other way this time. We've essentially started off, we've created an artificial signal composed of a sine and then outputted it to the microphone. Obviously, there's a lot that goes into the sound command that we don't talk about. I mean, this is more for computer hardware and computer technology, right? How does the computer essentially take this F signal and then convert that into something which then vibrates the drums for your speakers, right? And that's an interesting question in itself. Okay, now the very last thing that I want to just talk about before the second lecture, which is on the second part of the Math and Music lecture, is basically how the computer can obtain the Fourier spectra of this signal. And the computer that MATLAB uses, and most audio processing codes will use, what's known as a fast Fourier transform. And for this course, it's not too essential for you to know what a fast Fourier transform is, though you can look it up. As long as you understand that the fast Fourier transform, or the FFT, is a way that you can essentially send in this vector f, or f2, and for MATLAB to obtain for you the coefficients of the Fourier spectra, the weightings of the Fourier series, if you like, okay? And so I'm going to copy and paste that code in here, but I'm not going to explain the code. Well, I'm not going to explain it in great detail because it's not so essential for you to know, okay? But I'll walk you through little bits and pieces of the code. What this next section of code does from lines 22 onwards is mainly it constructs this y hat vector, which is the FFT of F2. F2 is the secondary signal that we created, the one that was 0.6 times the 440 hertz signal plus 1 times the 659.3 hertz signal. And essentially what y hat is that it's the Fourier coefficients, the AKs and BKs, or the ANs and BNs, but it's in complex form firstly, so it's in essence, an plus I times bn, but it's also rearranged. The vector has been rearranged in a bit of a funny way, and that's where I'm not going to go into detail. These next few lines of code rearrange the function so that it's in a way that we can visualize it. Okay? Essentially, the FFT function splits up the ANs and the BNs so that they run not in the order that you think they should. And so that's what these next few lines do. These next few lines will plot for you the output of the FFT function, or the spectrum. So this is what the spectrum looks like. You remember we introduced the terminology of spectrum, that on the x-axis, you can think of it as frequency, f, or k. On the vertical axis, you have the amplitudes of the sine and cosine components. In this case, you see that once you feed in the original signal into this FFT function, which constructs the Fourier series, then it produces a spectrum in Fourier space, which is exactly what you would expect. A peak at around 440 hertz. This is the A note on the spectrum. And then a peak at 659.3 hertz. This is the E note. Moreover, the magnitude of these peaks should tell you what the magnitudes you set for the original signal were. So, in this picture, the dotted lines, the dashed lines in the code, if you look at the code here, the dashed lines, I've simply marked for you where the locations are, 440 hertz and 659.3 hertz. So the dashed line, if I zoom in here to the picture, there you are. It's not quite exact, I think, because there might have been an error in my code where I shift the index. I think there's an error in the code where I shift the index by a +1. But that peak you would expect to lie right at 440 hertz. So I have to go and find that error in my code. Okay? And there's a similar peak at 659.3. You'll notice that the peak is not a single point, but it's composed of multiple points. And we won't go into why that is. It's essentially how MATLAB computes the Fourier series, the Fourier transform. Okay? So this is essentially where we're going to end this first lecture. It's a short lecture, but it's covered some important concepts for you. We've covered everything from this terminology of spectrum of Fourier space, thinking of k, bk, or k, ak, as equivalent to real space, or time, right? Instead of thinking of a signal in real space of f, or f of x, or in this case, t and f of t, you can think of it in terms of Fourier space, and in many ways, that is an equivalent representation of the signal. As you've seen here, that representation of the spectra has some powerful intuition behind it, that your signal might be very complicated, but you can still plot the spectra, you can still plot Fourier space, and by looking at the peaks, at where the peaks are the largest, that essentially tells you how your signal is decomposed into pitch. Okay? We talked about how sound is created, how you begin from a mechanical vibration of a string, how that's transferred through the air, how that makes it into your microphone, and then how that's digitized. We've also talked about this concept of frequency and sampling frequency, frequency measured in hertz and indicating how often the signal will repeat in 1 unit of time, 1 second, and sampling frequency, which is a natural limitation of your computers or of digital equipment to record continuous sound. It has to record it in chunks. That's the sampling frequency. We then took a very simple MATLAB script to create a vector of t and f of t, a simple sine wave which was composed of 440 hertz, and then played that for you. And you see that that sound, as simple as, creates this cool noise, right? And that's the thing that we interpret as sound. And then finally, we showed you how you can just create different kinds of functions f by weighting different sinusoidals with different amplitudes. And that creates an A note and an E note combined together. This is what we did. And then finally, this was a little bit rushed, but I showed you how using the f of t function in MATLAB, you can essentially construct the spectra.